There is a question that circulates in every serious defense analysis community in April 2026, and it refuses to be answered with a single sentence. Which fifth-generation fighter is superior, the F-22 Raptor or the J-20 Mighty Dragon? The reason it cannot be answered simply is because the question contains at least two entirely different questions inside it. The first is a technical duel question. In a one-on-one engagement at a specific range, with specific weapons, which aircraft survives? The second is a strategic campaign question. In a sustained air war over the Western Pacific, across hundreds of sorties, with an adversary with airborne early warning support and hundreds of aircraft, which side achieves air dominance? These two questions do not have the same answer. That divergence is where the real analysis lives. What this audit will establish, through the evidence rather than through preference, is the following. In an isolated engagement under equal external support conditions, the F-22 Raptor retains a decisive advantage, driven by its all-aspect stealth, its Supercruise capability, and the maturity of its radar and electronic warfare architecture. In a realistic Pacific conflict scenario as of April 2026, with both aircraft operating within their respective kill chains, with airborne early warning aircraft providing off-board targeting, and with the J-20 carrying a missile whose effective range exceeds anything currently operationally deployed on the F-22, the outcome becomes genuinely contested. Not because the J-20 is a superior aircraft, but because air combat in 2026 is no longer decided by the aircraft alone. The F-22 Raptor was designed from the outset as a very low observable platform in all aspects: frontal, lateral, and rear. Its airframe geometry, two-dimensional thrust vectoring nozzles, and radar-absorbent material coverage were optimized to present the smallest possible radar cross-section from every attack angle. Credible Western estimates place the F-22's frontal radar cross-section between 0.0001 and 0.0005 square meters, a figure roughly equivalent to a small bird or a large insect on radar. The lateral and rear aspects are larger, as they are on all aircraft, but the F-22's two-dimensional nozzle geometry and careful exhaust shaping provide substantially better rear stealth than most fifth-generation designs. The J-20's stealth profile is architecturally different and strategically revealing. It achieves very low observability from the frontal aspect. Estimates range from 0.001 to 0.01 square meters frontally, roughly 10 to 100 times larger than the F-22, but still within the low observable category. However, the J-20's canard configuration, conventional vertical tail surfaces, and early production circular engine nozzles produce a significantly larger radar cross-section from lateral and rear aspects. This is not a design flaw, it is a design choice that reflects the J-20's operational concept. The J-20 is built to penetrate a defended airspace from a specific approach vector, not to achieve stealth in all directions simultaneously. It is a frontal stealth-optimized platform, which is appropriate for an aircraft whose primary mission is long-range beyond visual range missile employment, a role in which the adversary's radar is almost always ahead of you. The practical consequence of this difference can be expressed in radar geometry. Using standard radar range equations and applying the estimated radar cross-sections of both aircraft to the capabilities of their respective radar systems, the AN/APG-77 radar on the F-22 can achieve detection quality sufficient for fire control on a J-20's frontal aspect at approximately 60 to 70 kilometers. The J-20's Type 1475 AESA radar, even with its larger aperture and newer gallium nitride transmit-receive modules, achieves fire control quality detection on the F-22's frontal aspect at approximately 20 to 45 kilometers. This gap, between 60 kilometers for the F-22 detecting the J-20 and 20 to 45 kilometers for the J-20 detecting the F-22 with its radar alone, is the fundamental stealth advantage that the Raptor holds over every other aircraft currently flying. The F-22's AN/APG/77 radar uses approximately 1,900 to 2,000 gallium arsenide transmit-receive modules. It is a mature system, first integrated into the F-22 in the late 1990s, and its signal processing architecture has been refined across 2 decades of operational service. Its primary distinguishing characteristic is not raw power, but low probability of intercept, the ability to radiate in ways that are extraordinarily difficult for an adversary's radar warning receiver to detect and characterize. The AN/APG/77 can illuminate a target with a radar signal that the target's own defensive systems may not recognize as a targeting emission until the missile is already in the air. In the language of electronic warfare, it is a weapon as much as it is a sensor. The J-20's Type 1475 AESA radar, in its latest production configuration, has transitioned to gallium nitride transmit-receive modules, a material upgrade that the F-22's radar has not yet completed across the fleet as of April 2026. Gallium nitride is more power efficient and more thermally stable than gallium arsenide, which means the Type 1475 can potentially generate higher average power output within the same thermal constraints. The radome of the J-20 is physically larger than the F-22's, providing a larger antenna aperture that translates to longer detection range. Against a conventional 1 square meter target, the Type 1475 can achieve detection at approximately 300 to 370 kilometers. Against the F-22's frontal cross-section of 0.0001 to 0.0005 square meters, that same radar achieves detection at 20 to 45 kilometers, a reduction that illustrates precisely why the F-22's stealth remains its most decisive tactical asset, even against a modern large-aperture AESA radar. One critical gap in the F-22's sensor architecture deserves direct acknowledgement. As of April 2026, the F-22 fleet does not have an integrated infrared search and track system. The IRST program, a contract awarded in January 2025 valued at approximately $270 million, is in flight testing, with production deliveries not expected until approximately 2028. The J-20, by contrast, has operated the EORD-31 IRST and EOTS-89 electro-optical targeting system since at least 2015, and has deployed a full-sphere electro-optical distributed aperture system since approximately 2023. This means the J-20 can search for, detect, and track aircraft without emitting any radar signal whatsoever. The operational consequence is that a J-20 flying in passive mode, with its radar off, can use its passive infrared sensors to search for the thermal signature of an F-22's engine exhaust at ranges that the stealth geometry of the F-22 cannot reduce, because stealth does not hide heat. Chinese manufacturer claims suggest the EORD-31 can detect the F-22 at approximately 110 kilometers in a tail aspect or high-contrast thermal environment. This figure cannot be independently verified and is almost certainly optimistic under combat conditions with countermeasures. However, the physics of passive infrared detection are sound. An aircraft with 2 large military turbofan engines operating at high power settings produces a substantial thermal signature that no shaping or coating can fully conceal, and the J-20's IRST operates at wavelengths entirely outside the range affected by the F-22's radar-absorbent materials. In April 2026, the most consequential asymmetry between the F-22 and J-20 is not stealth, not radar, and not engine performance. It is missiles. The F-22's primary beyond visual range weapon remains the AIM-120D3 AMRAAM, with a published maximum range in the neighborhood of 160 to 180 kilometers. The AIM-260 Joint Advanced Tactical Missile, which was designed specifically to match the range of China's PL-15, remains in development. Congressional funding for initial procurement appeared in the fiscal year 2026 budget request, and flight test Category C evaluations were underway in 2024. As of April 2026, AIM-260 has not achieved initial operational capability. The F-22 pilots who take off from Andersen Air Force Base to face J-20s over the Taiwan Strait do so with AIM-120D3 AMRAAMs. The J-20's primary beyond visual range weapon is PL-15. With a dual-pulse solid rocket motor, active radar terminal seeker, and published Chinese domestic range estimates of 200 to 300 kilometers, the PL-15 provides a J-20 firing solution at ranges where the F-22 cannot yet return fire with an equivalent weapon. The PL-15 can receive mid-course guidance updates from a KJ-500 airborne early warning aircraft, meaning the J-20 does not need to maintain its own radar lock on the F-22 throughout the missile's flight. It launches on an off-board targeting solution, goes silent, and the missile homes autonomously in terminal phase. The J-20 in this engagement sequence functions less like a dogfighter and more like a missile truck, a platform whose primary job is to place the PL-15 at kinematically advantaged range and then survive long enough to confirm the kill. The standard J-20 internal weapons configuration carries 4 PL-15 missiles in its main bay, with 2 additional PL-10 short-range missiles in lateral bays. A folding fin variant of the PL-15, demonstrated at the 2024 Zhuhai Air Show, potentially allows 6 PL-15s in the main bay, a significant increase in magazine depth for a platform designed for beyond visual range saturation. The PL-21, a reported ramjet-powered very long-range missile with claimed range approaching 300 to 400 kilometers, is likely too long at approximately 6 meters to fit in the J-20's main weapons bay without modification. It does not appear in credible assessments as a standard J-20 combat load as of 2026. The F-22's kinematic superiority over the J-20 with its earlier engines was one of the platform's most documented advantages. 2 Pratt & Whitney F-119 PW-100 engines, producing approximately 156 kilonewtons of thrust each, give the F-22 a thrust-to-weight ratio of approximately 1.37, one of the highest of any operational aircraft. This enables the F-22 to supercruise at approximately Mach 1.5 to 1.8 without afterburner, meaning it can reposition across the engagement envelope, manage its energy state, and choose the conditions of an engagement in ways that afterburner-dependent aircraft cannot sustain. The 2-dimensional thrust vectoring nozzles add post-stall maneuverability that remains unmatched in within-visual range combat, the ability to point the aircraft's nose at a target that is already behind it, or to perform maneuvers that exceed the aerodynamic limits of conventional control surfaces. The WS-15 engine has materially changed this calculus. Serial production of the WS-15 was confirmed by 2023, with J-20A airframes equipped with the new engine appearing in photographic evidence from 2024. The WS-15 produces an estimated 180 kilonewtons of thrust per engine, a figure that gives the J-20 a total thrust output exceeding the F-22's for the first time. J-20 demonstrators and production aircraft equipped with WS-15 have demonstrated supercruise capability in the Mach 1.4 to 1.8 range, substantially closing the kinematic gap with the Raptor. What the WS-15 does not provide as of 2026 is thrust vectoring. The nozzle of the WS-15 is a serrated fixed design that reduces radar cross-section from the rear aspect, a meaningful stealth improvement, but does not offer the post-stall maneuverability that the F-22's 2-dimensional TVC provides. In within-visual range combat, this remains an F-22 advantage. The J-20 with WS-15 is a fast, long-range, high-energy platform optimized for beyond visual range engagement, not for the knife fight that the F-22 was built to dominate. The combat radius differential deserves equal emphasis. The F-22's combat radius is approximately 850 kilometers without refueling. The J-20's combat radius approaches 1,800 kilometers. In the geography of a Taiwan contingency, where American air power must operate from Guam or Japan, while Chinese air power operates from mainland bases, this differential translates directly into sortie rate, persistence, and the ability to sustain pressure across the engagement timeline without cycling back for fuel.
The engagement calculus described above, stealth detection ranges, missile kinematics, individual aircraft performance, represents what analysts call the platform-centric assessment. It is necessary but insufficient for understanding the actual combat outcome in a Pacific conflict. What changes the calculus fundamentally is the kill chain, the integrated sequence of detection, identification, targeting, engagement, and assessment that modern air forces execute not through individual aircraft, but through networks of aircraft, ground-based radars, satellites, and data fusion systems. The J-20's kill chain runs through the KG-600 carrier-based and KG-500 land-based airborne early warning and control aircraft. The KG-500, operating at patrol altitude several hundred kilometers from the engagement area, can detect the J-20 itself with its own radar and provide track data to J-20 pilots via data link. More critically, it can attempt to detect the F-22 at ranges that the J-20's own onboard radar cannot achieve, using its larger antenna aperture, lower operating frequency bands that are less affected by the F-22's radar-absorbent coatings, and multi-static detection geometry that exploits returns from multiple angles simultaneously. Chinese technical claims attribute detection ranges of up to 250 kilometers for the KG-500 against stealth targets. The physics for a single platform against a target with an RCS of 0.0001 square meters do not support this figure at conventional radar frequencies. More credible assessments place the KG-500's effective detection range against a frontal F-22 at 30 to 70 kilometers, meaningful for cueing J-20 pilots into the engagement area, but not sufficient to provide fire control quality targeting data for a long-range missile shot. The multi-radar fusion architecture that China claims dramatically improves this figure is theoretically sound, but has not been validated in operational conditions against genuine stealth targets. The American kill chain operates through the E-7 Wedgetail's MESA radar, which provides detection of J-20 class aircraft at approximately 100 to 180 kilometers. Unlike the KG-500's challenge in detecting the F-22, the E-7's challenge in detecting the J-20 is more manageable. The J-20's lateral and rear aspect RCS is substantially larger than its frontal aspect, and the E-7 is not always looking at the J-20's nose. The F-22 uses the multifunction advanced data link to receive off-board targeting data in a communications architecture specifically designed to be difficult to detect and jam. In the contest between kill chains, not aircraft, the American architecture has the edge in electronic warfare resilience and data link security, while the Chinese architecture has the edge in sensor quantity and geographic density of the surveillance network.
At ranges between 150 and 250 kilometers, the engagement favors the J-20 in the current configuration. The J-20 can receive a targeting cue from KJ-500 at the outer edge of this envelope, launch a PL-15 in silent mode without activating its own radar, and the F-22 has no comparable weapon to return fire. The AIM-120D3's maximum kinematic range of approximately 160 to 180 kilometers is at the lower end of this band, and achieving effective probability of kill at maximum range requires firing conditions that may not be achievable if the F-22 does not have precise targeting data. The first shot advantage at this range band belongs to the J-20 by virtue of missile range alone.
At ranges between 50 and 150 kilometers, the engagement becomes more contested. The APG-77 LTE achieves fire control quality detection on the J-20's frontal aspect at 60 to 70 kilometers. The J-20's IRST may be detecting the F-22's thermal signature at comparable or somewhat greater ranges in ideal conditions. Both platforms can now fire their primary weapons. The F-22's Supercruise allows it to maneuver the engagement geometry to its advantage, choosing to close the range rapidly where its kinematic superiority matters, or to disengage if the tactical situation is unfavorable. At this range band, the F-22's stealth and sensor fusion give it a marginal first-shot probability advantage, but the exchange is genuinely close. At ranges below 20 kilometers within visual range, the F-22 is the dominant platform. Thrust vectoring, high thrust-to-weight ratio, mature sensor fusion, and the energy management advantages of Supercruise capability give the F-22 a post-stall maneuverability envelope that the J-20 without TVC cannot match. The F-22 lacks a helmet-mounted display across the fleet as of April 2026. The Scorpion HMD integration is still in progress for select units, which partially limits its exploitation of the AIM-9X high off-bores head capability. The J-20 has a helmet-mounted display and the PL-10 short-range missile with high angular off-bores head capability. Within visual range combat is high risk for both aircraft, but the kinematic advantages favor the F-22. In a scenario where both aircraft operate with full airborne early warning support, the contest shifts from individual aircraft performance to kill chain integration speed vital. The side that can detect, track, and generate a fire control quality targeting solution and transmit that solution to a shooter aircraft with a missile that can reach the target wins. Both architectures are capable. The question is, which degrades faster under electronic warfare pressure? The American answer is a data link architecture designed from the ground up for contested electromagnetic environments. The Chinese answer is sensor density. More radars, more platforms, more overlapping coverage that makes any single jamming source less effective. In a war of attrition over weeks and months, the fundamental calculus changes entirely. The F-22 fleet numbers approximately 183 operational aircraft. Production has ended. Congressional action has prevented the planned retirement of 32 Block 20 test aircraft, preserving them in the inventory, but no new F-22s will be produced. China is currently manufacturing the J-20 at approximately 100 to 120 airframes per year, with a fleet that has already exceeded 300 aircraft and is growing. In a high-attrition air campaign where aircraft are being lost to surface-to-air missiles, accidents, and combat, the side that can replace losses faster wins the long engagement. The F-22 cannot be replaced. The J-20 can.
The evidence supports two conclusions that are simultaneously true and cannot be collapsed into a single answer. In an isolated one-on-one engagement between these aircraft, in the BVR regime where both platforms are most likely to operate, the F-22 holds a meaningful advantage at ranges where the AIM-120D3 and the PL-15 overlap in effective employment range, approximately 80 to 160 kilometers. Its stealth gives it a detection geometry advantage. Its radar gives it a fire control quality solution before the J-20's radar can achieve the same. Its supercruise and kinetic performance give it the ability to choose the geometry of the engagement. In within visual range combat, the F-22's thrust vectoring and energy management make it the dominant platform. The F-22 wins the duel. In a realistic Pacific campaign scenario in April 2026, the J-20 is a more dangerous adversary than platform-centric analysis suggests. Its IRST operates in a domain the F-22's stealth cannot address. Its PL-15 outranges the AIM-120D3 that remains the F-22's primary weapon, because the AIM-260 that was designed to close this gap is not yet operationally available. Its combat radius of approximately 1,800 kilometers versus the F-22's 850 gives China a sortie generation and persistence advantage in the Western Pacific's specific geography. its production rate of 100 to 120 aircraft per year versus a U.S. fleet that produces 0 new F-22s means every exchange that trades F-22s for J-20s on a one-to-one basis is a strategic victory for China. And its integration with a dense airborne early warning network provides targeting cues that make its missile range advantage exploitable in practice rather than merely theoretical. The F-22 wins the duel. The J-20 wins the campaign, not by being a better aircraft, but by being the right instrument for the strategic environment China has constructed around it: long-range, networked, numerous, and replaceable. The most important weapon in the comparison is not on either aircraft. It is the AIM-260, which the United States has not yet delivered to operational units. Until it does, the F-22 faces an adversary with a longer sword in a fight where reach determines who strikes first.